Space, the final frontier.
Oh, hello there, and welcome to our production. Humans have always been intrigued by the world around us, and this includes the vast space beyond this planet, which is the last to be explored. However, the beginning of space exploration started at the dawn of man. In fact, it may be the oldest science. Certain constellations, such as Scorpio, trace their origins back before 3000 BC. These constellations were used as a part of folklore to provide entertainment and as a celestial calendar for time management. It was the ancient Greeks who started studying the universe in depth. Aristotle and company developed the geocentric model of the universe, and with minor additions by Ptolemy in the 2nd century, it has remained the dominant theory for over 2,000 years. All of these observations of the planets and stars were made with the human eye. This unaided type of observation was limited, to say the least, yet with careful study and documentation, many correct assessments of the universe have been made. Even the groundbreaking theory presented by Copernicus in the 1500s was made solely by the human eye. But human curiosity drove scientific advances, such as the telescope, around the 16th century to help gain a clearer view of the stars. Galileo, being one of the first astronomers to use the device, was able to prove Copernicus's theory, and was also able to make observations that could not be seen with the human eye. He could determine the height and the depth of craters on the Moon, Jupiter, sunspots, phases of Venus, and many other stars. His equipment was very primitive, though. Originally, it could only magnify to 8 times before being upgraded to 20 times. It also had a relatively small field of view, roughly half of that of the Moon, and required precise placement for proper observation. Since then, telescopes have continued to advance in order to increase the field of view as well as the magnification. Modern telescopes demonstrate magnifications over 7,000x, and a field of view much larger than the original. These better telescopes require massive and complex lens structures. These lenses have been the limiting factor in the progression of telescope improvement. It's only recently, in the last 100 years, that these lenses have been able to be precisely crafted. Continuous improvements and advances are always being made, including the super-large telescope lenses used today, the processing of which will be described later. Other space exploration methods have been developed in the last century as well. All of these active techniques, such as physical probes, manned travel, and electromagnetic emissions, provide otherwise unobtainable information on the stars. Despite the vastness and hostility of space, man will one day traverse it. Until then, passive techniques such as telescopes will be used to gather information as well as take breathtaking images. Thus, as stated earlier, the last unexplored vast areas are in space, the final frontier. The first telescopes were made of 2 convex lenses, an objective lens at the front of a simple tube and an ocular lens located near the rear. Eventually, a third convex lens was added between the 2 original to increase magnification and adjust the orientation of the image to its actual position. A telescope has 2 general properties: how well it can collect light and how much it can magnify the image. A telescope's ability to collect light is directly related to the diameter of the lens that is used. Generally, the larger the aperture, the more light the telescope collects and brings to focus, and then the brighter the final image. The telescope's magnification depends on the combination of lenses used. The eyepiece performs the magnification. The objective lens collects light from a distant object and brings it to a point or focus, where the ocular lens takes the light from this focus and spreads it out to magnify the image. Historically, telescopes have been made with hand-blown glass lenses that are then assembled into a soft metal tube. Modern techniques employ injection molding, generally of plastics, to make the exterior of the telescope. Next, the glass must be made. This is done by mixing and heating the proper raw materials with waste glass, otherwise known as a cutlet. This molten glass is then poured into molds with the same shape as the lenses required. Once the optical glass blanks have been constructed, they must be processed through a method of cutting, grinding, and polishing. During cutting, a high-speed rotational circular cutter with a round diamond blade called a curve, generates and shaves the shape of the lens to a close approximation of the desired tolerance. The cut blanks are then placed on a curved block where the surfaces line up as if they were part of one large spherical curve. This is necessary so that the grinding machine can grind all of the lenses uniformly to match the final product. The ground blanks are then taken through the polishing process. This is similar to the grinding process, but instead of an abrasive, a slurry containing a polishing substance such as cerium dioxide in the form of a very fine pink powder is used to get the lenses within their final tolerance. In an effort to peer even deeper into the depths of space, Earth-based telescope designs, such as that proposed for the Giant Magellan Telescope, or GMT, are becoming more and more grand in their scale, and new technologies were needed to produce mirrors of the appropriate size and tolerance. Under the stadium at the University of Arizona, Dr. Roger Angel is leading the way with a novel production method called spin casting. Spin casting begins with a mold that is filled with chunks of cold solid glass as opposed to a molten mold. In the case of the GMT project, this mold is a massive 27 feet across, limited only by the size of roads and the building it's processed in. The furnace is heated to 2100 degrees Fahrenheit to melt the glass and is simultaneously spun at a rate of 5 revolutions per second. This spinning helps ensure the glass melt will flow into the parabolic shape of the mirror that it will eventually become. To prevent cracking and the formation of residual stresses, the melt stays in the oven and slowly cools over a period of 2.5 months until it reaches room temperature. Once it's cooled, the mirror is ground down to within 100 microns of its final shape. This grinding, however, is not nearly close enough to the end shape. The next step in the process is to polish the mirror to extremely high tolerances within 25 nanometers, or approximately 1/millionth of an inch. This is made even more difficult as the surface of the mirrors for the GMT are aspherical, which is necessary to focus the light to the correct spot once it's mounted within the telescope assembly. To make these tolerances possible, the polishing is done by an automated system known as the large polishing machine, in a process that can take up to a year to complete. This automated process will be used in the future on other optical systems outside of telescope work. A specially designed laser contour mapping technology is used to check these tolerances, which a human eye could never detect. Now, my former colleague Wendy Campbell from the Carnegie Institute of Science has something to say.
Opportunity for new discovery in astronomy generally follows when we make a big leap in resolution or sensitivity like this.
And all of this majesty is just around the corner. The mirrors for the GMT are currently under production, and the telescope is expected to see first light in 2020. So the next time you gaze and wonder at the night sky, just think of how much closer you could gaze with a massive telescope. Thank you, and good night.